Okay, welcome back, everybody. It's just about time to begin. So I'd like to welcome our next speaker, Ilias Kotsireas from Wilfrid Laurier University. And he is going to tell us about 20 plus years of Legendre pairs. So over to you, Ilias.
Thanks, Mark. Is the sound okay?
Yes, it's perfect.
Thank you. So I would like to start by thanking Professor Tufik Mansour for inviting me and for organizing this conference, and also the local organizing committee, of course, for all the efforts. So I would like today to talk about various developments in this topic of Legendre pairs over the past 20 years, and I will start with two ingredients that we need to define Legendre pairs. The first ingredient is this periodic autocorrelation function, abbreviated as often as PAF. What it is that you take a finite sequence with n elements, and you do a cyclic permutation by 1, by 2, by 3, or by s in general, and then you take the inner product of the original sequence and the cyclically permuted sequence, and this is a definition of the PAS of the periodic autocorrelation function. Of course, this index here is taken mod n. What's the connection of this periodic autocorrelation function, which is very well studied by engineers, right? They sort of invented it. So if you have a circulant matrix CA, whose first row is equal to your sequence, your finite sequence A, then the periodic autocorrelation function is the inner product of the first row and the ith plus 1 row. There is also a symmetry property, so essentially, which says that in order to know the periodic autocorrelation function values of a finite sequence, we need to know half of them because the other half are equal. Then there is the second elementary symmetric function property, which says that if we sum them up, all of them, these n-1 values, except the value at 0, because this is just the sum of the squares of the sequence. So if we sum up all the periodic autocorrelation function values, we end up with twice the elementary symmetric function in the elements of the sequence. The second ingredient that we need in order to define Legendre pairs is this concept of power spectral density, sometimes abbreviated as PSD. Of course, PSD has other meanings, positive semi-definite, and etc. But here it means power spectral density. So what we do here is that we take the discrete Fourier transform associated to a sequence with the usual definition, where this omega is the primitive nth root of unity. And if we denote the DFT of a finite sequence by this notation here, mu0 up to mu n n-1, then if we take the square magnitudes of these elements of the DFT, i.e. the sum of the squares of the real part and imaginary part squared, then this is the PSD coefficient for this argument k, and k goes from 0 to n-1. So this is the second ingredient. Again, just to summarize, we have the PAF, the periodic autocorrelation function, and the PSD, the power spectral density, which is just an easy computation associated to the DFT. And now with these two ingredients, we can give the definition of Legendre pairs, which is originally due to Sieber in 2001, therefore 20 plus years of Legendre pairs. If we have an odd n, then two sequences A and B over here, whose elements are restricted to -1 and +1, they form a Legendre pair that we also denote sometimes by LPN. So we parameterize by the length of the sequence, or order. Those two terms are also used. So it is a Legendre pair. These two sequences form a Legendre pair if the periodic autocorrelation function values sum to this constant -2 for every s from 1 to n minus 1 over 2. Remember, we only need to work with half the path values because of the symmetry property. So this is a definition of Legendre pairs. And typically, we do this normalization. We take the sum of the elements of the sequences to be equal to 1, because it helps with computations. And also, we kind of don't want to end up with many equivalent Legendre pairs if we don't do this normalization. And also this normalization leads to an upper bound on potential AB sequences, which is this one here, binomial coefficient, n over n plus 1 over 2. It's a Catalan-like quantity, if you like. And there is another consequence or property, which is that the constancy of the path values to minus 2 implies the constancy of the PSD values of A and B, but now the constant depends on n. So we have this relationship here. The PSD coefficients of A and B, if we add them up, they always give to n plus 2. The proof of this fact is done via this well-known Wiener-Khinchin theorem that essentially says that the DFT and the inverse DFT connect the path values and the PSD values. So to summarize again, Legendre pairs are characterized by the constancy of these two invariants, the path and the PSD invariants. If you like, the path constant is minus 2 and the PSD constant is 2n plus 2. So it's a very, very simple definition, I would say. And here are some examples just to make this concept more concrete. So for n equals 11, so an LP11 will have a PSD constant of 24. Here's A and B, the sequences. The first 5 path values are all equal to minus 1, and the same for B, so the sum is always minus 2. It's a sort of a trivial solution. If you move on to another prime 13, then LP13 is shown over here. The PSD constant is 28. You see the first 6 path values are 1 and minus 3, and underneath we have minus 3 and 1, so that the sum vertically is always minus 2. And here's a bigger example, a bigger prime. Again, this is A and B. They form a Legendre pair, and now these are the PSD values all the way down to 18. So that you see that when you sum them up horizontally, you always get the PSD constant 76. And here is a much bigger example, n equals 55. Now the PSD constant is 112. So if you think about it, what we have here is 110 binary variable. So it's computationally, it's a hard problem. And you see that the first 27 path values are more irregular. Now you have 9s, 5s, and so on, minus 3s, 7. But again, if you sum them up vertically, you always get minus 2. So this is a Legendre pair of length 55. And well, constructions, what kind of constructions are available for Legendre pairs? The first one is that for every prime length, there is a Legendre pair of order P via the Legendre symbol from number theory. So this is a small maple code to illustrate this construction. You take the sequence of the Legendre symbols, I over P, for I from 1 to P minus 1. You prepend 1 here to make this A sequence. And again, you prepend 1, but now you take minus this sequence over here, the sequence L. And then A comma B is a Legendre pair of length P for every odd prime P. But not all primes are the same. There is an interesting behavior that occurs according to the parity of P mod 4. So the mod 4 dichotomy. If P is 3 mod 4, then all the path values are equal to minus 1. All the PSD values are equal to plus 1. So we get the path constant minus 2 and the PSD constant 2P plus 2 that we wanted. If P is 1 mod 4, then all the path values belong to 1 and minus 3. There are only 2 different PSD values, and there is a formula that I learned recently from Arne Winterhoff in Austria. this formula uses a Gauss sum interpretation. And so again, we get the two constants, the -2 and the 2p + 2, but they materialize somewhat differently. Then there is another construction, the twin primes construction. So for every twin primes p and p + 2, there is a Legendre pair of order p times p + 2 now. And there are two caveats in this construction. The first one is that, well, it relies on the twin prime conjecture. And if the twin prime conjecture from number theory is true, then this yields an infinite class of Legendre pairs and the closely related Hadamard matrices that I will get to in a minute. And the second caveat is that the twin primes must have a common primitive root. And this is not so obvious. This is in fact an open problem in number theory. There is no known counterexample, so it's most likely true. These are the construction details. If you call G this common primitive root of p and p + 2, then you set these parameters, then the positions of the -1 in the sequence that will make the Legendre pair are encoded by this formula down here. So this is the twin prime construction. And well, what's the motivation behind Legendre pairs? Basically, it's the construction of Hadamard matrices. So if we think about the Hadamard conjecture, which is open since 1893, there is a Hadamard matrix of order 4n for every n, 1, 2, etc. The smallest open orders are Hadamard matrix 668, 716, and 892. And the computational state of the art in this Hadamard conjecture, if we look at in 1985, the smallest open order was 268. It was found by Savade. And then 20 years later, the smallest open order was found by Karagani and Taifer in 2005. And then another 3 years, Djokovic found Hadamard matrix of order 764. And we contributed another one of order 1004 in 2014. Salom Eliahu here has a very nice survey in this online mathematics encyclopedia of CNRS that you can find online on the Hadamard conjecture. So what is the connection between Legendre pairs and Hadamard matrices? The connection is the two circulant cores construction. So essentially, if we have a Legendre pair of order n, so A and B, then we make two circulant matrices, CA and CB, by using A and B as the first rows. And then we put them into this template array over here, where plus means -1. Plus means +1 and minus means -1. And then this matrix of order 2n + 2 is a Hadamard matrix. So if you remember, we had LPP, Legendre pairs of order p for every prime p. So that means that we get Hadamard matrices of order 2p + 2 for every prime p. And similarly, from the twin prime construction, we get Hadamard matrices of 2 times p + 2 + 2. So in other words, one way to think about it is that Legendre pairs sort of furnish a structured version of the Hadamard conjecture. If you can exhibit a Legendre pair for every odd number n, then because the range of values 2n + 2 as n ranges over the odd integers is, of course, the range of multiples of 4, you end up proving the Hadamard conjecture, but via this very structured form of the Hadamard matrix. When n is not a prime, well, then we have to do something else, or a product of twin primes. And so we introduced this concept of compression of Legendre pairs in 2015 with Dragomir Djokovic. So if a sequence has an order V, which is a composite number D times M, then we define these subsums over here of elements of the sequence which are located D apart, and we put all of them together in the new sequence AD of length D, and we call this the M compression of the sequence A. So what we can easily see is that if we look at the M compression of a Legendre pair of order V by the same number M, which must be a divisor of the order, then we have two sequences of length D, and the alphabet increases now. The alphabet is from -M to +M. And these sequences have the property that they have a constant path -2 times n. So we see a linear scaling of the path constant from -2 to -2 times m, and the PSD constant is the same. It remains the same as the PSD constant of the original sequence. So to summarize, the M compression of Legendre pairs has the effect that path scales linearly and PSD remains invariant. Here's an example of compression just to fix the ideas. For an LP15, 3 times 5, the 3 compression gives these sequences of length 5. You can see the pattern. You just start with A0 and you add 5, and then you add another 5 and so on. So every element here is a triplet of elements of the original sequence, and 5 compression similar. You get these two sequences of length 3, where every element is the sum of 5 elements of the original sequence. So the question is, why is this interesting? Why we do that? Well, here's an example. For an LP133, which is 7 times 19, if we compute the 19 compression, we end up with these two small sequences of length 5 here. They have these properties listed here, okay? So they have path -38 and PSD constant 268, the same as the original sequences. But now, what if someone gave us these sequences A7, B7? Then can we recover the Legendre pair? Of course we can. This is the process called decompression. It is computationally expensive, but it's better than looking in a search space of, that is governed by this parameter 133. The problem with compression is that it's not a one-to-one mapping. And that means that if we find some other sequences of length 7, A7 tilde and B7 tilde, with these nice constants, the -38 and the 268, it doesn't mean that if we perform decompression, they will return this Legendre pair, right? But there are some ways to go around that. But in any case, compression has been used to find many new Legendre pairs and other combinatorial designs in the past 7 years or so. I want to come now to a few papers that we wrote recently. The first one here is the DCC paper in 2021, where we contributed the only known Legendre pair of length 77. This was done, this is work done out of the PhD thesis of Jonathan Turner, who works at AFIT in Ohio. We exploited the idea of simultaneous decompressions for Legendre pair. So what does that mean? It means that, for example, 77 is 7 times 11. So we can do 2 compressions simultaneously by 7 and by 11 and try to do some sort of matching algorithm using these binary matrices with fixed row and column sums. And all of that worked. Jonathan came and visited me here in Canada. So we ended up finding this LP77, which was an open problem since 2001, and some people even believed that it may not exist, but in fact it does. And as a byproduct, we also, when we look at this solution, which is very rare, but it exists, and we found it. If we do an 11 compression of this, then we see this path constancy property. What does that mean? It means that this is A7 and B7. These two sequences are the 11 compression of this Legendre pair of order 77 that we found. And if we compute the path values for each one of them, we only need 7 minus 1 over 2, 3 path values. You see that they're constant, -21, -21. And over here, the same, we compute the path values, we get 3 minus 1s. Of course, the sum is equal to -22, as it should. but we see that the path values they have this very specific property. This cannot be an accident, right? And in fact, we elaborated this this behavior of the path constancy property for an arbitrary divisor M of L of the length of the Legendre pair in this recent paper on the Journal of Combinatorial Designs 2021 with Christoph Kutzan. What we proved is the following theorem. If the M compression of AB, so this calligraphic A and calligraphic B, is made up from two constant path sequences of length n, and that means that the path values all the way through to n-1/2 are equal for A, for calligraphic A, and the same for calligraphic B, then the PSD values at integer multiples of M of the original sequences A and B are integers, exact integers. And moreover, we found the explicit evaluations of these exact integers in terms of the compressed sequences. So the PSD A, M times S is equal to the second power sum of calligraphic A minus the first path value, and the same for the B sequences. And computationally speaking, this is a criterion that can be used with, it's very efficient criterion that we have used in the code that we wrote, and we ended up finding a whole bunch of new Legendre pairs, and now the state of the art, computationally speaking, for Legendre pairs in the range less than 200 consists of these 12 integers down here. And we also, in that paper with Christoph Kutzan, showed how to determine the complete spectrum of the L/3, the L/3 value of the PSD coefficient. In other words, for here's a sample result. So we have an algorithm that does that. And this algorithm yields the complete spectrum. So for instance, what kind of result we proved? For L equals 117, 3 times 39, we know that PSD A39 and PSD B39 can only be one of these three pairs. Okay, that can be proved, and this can be done for every other multiple of 3. So this gives us a lot of information that we can exploit computationally. For example, to parallelize each one of these pairs can give a separate, program. So it's a layer of parallelization that we also exploited in our code. And another recent paper, which is submitted or in progress, I should say, it's Legendre pairs of length L multiples of 5. In this case, we have a conjecture. We have a conjecture that says that if the order or length of the Legendre pair is a multiple of 5, then there exist Legendre pairs of length of this length, so that the PSD value of A at L/5 and B L/5 is equal to L plus 1. So L plus 1 for A, L plus 1 for B. And then we have plus or minus this irrational number times this X. And again, by exploiting this conjecture computationally, it's an unproven conjecture, but we suspect highly that it holds. So we reduced the state of the art in these 10 integers now, and so the smallest one is 115. And if you look at these 10 integers, of course, half of them are multiples of 5, so they belong to the context of this conjecture over here. And well, the last topic I want to mention, I really want to keep the time, is multiplication theorems in the context of Golay pairs. So Golay pairs are pairs like Legendre pairs, but instead of the path constant being -2, they satisfy the condition that the aperiodic autocorrelations now sum to 0 instead of -2. What we do with them is that we use this discrete generating function, sometimes called the whole polynomials in design theory, which is, of course, this one here. So if Turing's multiplication says that if A and B are a Golay pair of length Z and CD is a Golay pair of length V, then the product pair EF is a Golay pair of length GV, and E and F are defined over here. They're kind of difficult to find, I guess, but somehow he did it. That's Turing multiplication. So we also observed with Djokovic that, in fact, if you weaken this condition, if you make CD a periodic Golay pair, so now two sequences whose periodic autocorrelation sums to 0, then the Turing's pair is also a periodic Golay pair of length GV. So I'm just showing this to sort of give you a flavor of the kind of multiplication theorems that are useful in this area. And well, it is an open problem to find, for example, multiplication theorems for Legendre pairs. They don't seem to exist. And that's the end of my talk. Thank you.
That's great. Thank you, Ilias, for a very nice talk, and for keeping on time also. It's appreciated. Are there any people who might have a question or two?
Yeah, I have a quick question. I'm Doron. At first, the motivation came from the famous Hadamard conjecture.
That's right, Doron. Yes.
Yeah, and the name Legendre pair because of the special case of the Legendre symbol.
Yes, that is correct.
And is a so-called quadratic reciprocity theorem useful part of it? Because relating.
Well, not that I know of, but
okay.
You know, maybe some new construction, for example, to imitate the twin primes construction, make it more general. Maybe quadratic reciprocity could be useful there, but I'm not sure. It's something to look at.
Thank you. Very interesting.
Thank you.
Thank you, Ilias, again, for a very nice talk.